All right, we're gonna start. So in the last lecture we started, and I think we're finishing up how we can go about describing a bunch of data according to some measure of location. And usually the ones that we care about are focused on centrality, okay? So that's like the mean and the median. So like where's the middle of the distribution? Along with that, we sort of discussed the pluses and minuses of each. So when we are doing a sample mean and we've collected a lot of data, basically what we're doing is we're just adding up all those values together and then dividing by the total number of values. Now the issue with this is that if we have an outlier value or multiple outlier values, that might really skew our average value. And then the question begins, or the question that gets sort of brought up is, does that average value or does that mean represent something meaningful to us? Okay. And so that was a little bit problematic. So to get around this, some folks suggest using the median, which again is where you just take the middle value of all the data that you have. If you have an even number of data, then you take the two middle values and then you average them together. The strength of this is that it's sort of robust to outliers. Okay, so like if you do have these outliers, then you'll be fine taking the median and it will give you a better indication of where most of your data lies. The issue, or actually one issue with that, could be that you actually hide tails that aren't even necessarily outliers, actually. So let me give you a case. So let's say I asked for the average, I asked 10 folks, what's your income? All right. And I got the following values. So maybe 15,000, 20,000, I don't know, 17,000, 16,000, another 15,000, right? And then I got something like 1 million, right? 2 million, 3 million, 4 million. Actually, let's just say, how many do I have there? 1, 2, 3, 4, 5, 9. So let's just say I asked 9, okay? If I take the median of these 9 values, what do I end up getting? I think the median here ends up being 20,000, okay? And so this is kind of problematic, right? At some level, we're not getting a good representation of our data. And in fact, the same issue occurs when you're taking mean, right? If you have a bimodal distribution and you're trying to represent that data with a single number, you're going to miss out somehow, right? So in this case, if you were to take the median of the data would be 20,000. If you were to take the average, I suspect the average would be over 1 million, all right? So which is it? Which is the right answer? And the problem is they're both sort of right? Because we have one cluster of incomes that are around, 15 to 20,000, and then we have another cluster that are in the millions. Okay? And that's the issue of making an attempt to just describe a distribution or data with one value. It's never going to work. So one of the things that I mentioned is that a lot of times what people do is they actually provide both measures. So they'll give the sampled mean and the sampled median, and it will give you some indication of what the data looks like, if it's negative skewed, positive skewed, or maybe even symmetric. So that's pretty useful. Now, if you do have something really weird going on like this, then what you should be doing is giving the histogram. That's my personal view. Because what we mentioned is there's probably something more complicated going on. And it's important to understand what that is. Right? And so here I think this basically mirrored that example where we have salaries of graduates from law school. Right? So, and what we saw were the mean and the median were actually pretty useless, right? They were both around 100,000, or I don't know, I suspect, maybe the medians, I take that back. The median's probably, actually that's a good question. Median still might be around 90K, right? But they're both not too far from each other. But what happens is we have a bimodal distribution, and so weird things are happening. And so really giving a frequency diagram or a histogram is much more useful. All right. So one way that we can totally get rid of the issue of outliers is to do something called the trimmed mean. And again, the basic idea is we trim off the smallest and largest values in our data set, and then we take an average of whatever's left over. Yeah, this works. This is actually kind of nice for some regards, especially if you're, let's say, trying to describe a general trend. I think a trimmed mean might have some value, right? So like, again, I'll bring it back to aviation in the field that I work in. If I'm trying to talk about what is the average delay, it might make sense to trim off the top 10% and the bottom 10%, okay? The reason why I trim off the top 10% is because that's when things go really bad, right? Flights get canceled, or you have a hurricane going through or something like that. And so the question is, how meaningful is that top 10% to the actual question of being like, hey, what are the odds that you go to the airport and your flight is delayed 10 minutes, 20 minutes, right? That's way outside the realm of hurricanes and all that stuff, right? So in that sense, it's sometimes an appropriate measure to use a trimmed mean, right? I don't fault people for doing that. I think it's a little bit weird whenever you delete data, right? Because for me, deleting data seems like you're trying to hide something, okay? Okay, so another thing people like doing, and I think we started to touch on this before we wrapped up the last lecture, is on percentiles and quantiles, okay? So I think everybody here took the SATs, right? Actually, no, not everybody. Yeah, that's right. Okay, some of y'all took the SATs, right? And when you get your score back, your score is actually determined based on how well you did in comparison to everybody else, right? So if you did better than 99% of everybody else, I think the score that they give you is a perfect, right? Or whatever, perfect 800. I know this for a fact because I absolutely got some problems wrong when I took the SATs, but I still ended up with an 800 in math. So you can still get problems wrong and end up with a quote-unquote perfect score. I think I don't know what they define the median to be. I think 50%, you're around like 400 to 500. They might have changed it recently. And so this is one way of measuring sort of the spread of the data, okay? And so in Excel, we can actually do this quite easily, right? So we might ask questions like, okay, what's the lowest 5%, right? What's the greatest 95%? And what we're really trying to do, so I'll do this using a normal distribution because I think most of y'all are used to seeing a normal distribution just in your own, if you've, let's say we have some distribution like that. And let's say this is the height of students at UCF. I don't know. Okay. And so I don't know what the average height would be. Does anybody want to take a guess? Average height?
5'9".
5'9"? Oh, no. Shorter than 5'9". Why is it shorter than 5'9"?
5'6".
What assumption is he making?
Oh.
They're all males, yeah.
Actually, it's like around 5'8". It's only like 5'8", 5'7" for males.
Yeah. So I don't know, let's say it's 5'5"?
I feel like a lot of people here are tall.
It might be.
Not-
Well, so we have competing issues, right? Because I think most colleges have about 55% women. Yes, sir.
Could this also be like a bimodal thing if you were talking about?
It could be. So I would venture to guess that if you were to look at men, it's some spread like this, let's say centered around 5'8", 5'9". Okay. That's horrible handwriting, sorry. I think it's 5'8". And I suspect if you were to look at women, what was the number thrown out for women? Because I think that was about right. 5'5"? It might even be shorter than that. Yeah, but it's not too far off. So I'm gonna go 1 inch shorter and say 5'4". Okay. All right. So that's what you get. Now the problem is if we add all those heights up together, we probably end up getting something like this. Yeah. The reality is, I think most colleges have 55% female because women tend to do better academically, which is something. It's weird because nobody likes talking about it, right? So usually, so I go to these education policy conferences, and usually one of the things that we talk about is how do we get first generation college students doing well? How do we get low income students doing well? How do we get underrepresented minorities doing well in STEM? How do we get underrepresented women in computer science doing well? But nobody wants to talk about how do we get men to do better in college. It's this weird thing. I don't get it. But yeah, go women, right? You guys are rocking out like at every level. It's really impressive. Anyways, and this actually I think probably what we'll do at some point later on in the semester, we're going to talk about this problem. Oops. Come on. Of if I were to give you the height of a student, could you tell me whether it's a male or a female student? It actually ends up being pretty hard. If I were to tell you I have a student who's 6 foot tall, what would you guess? Male or female? Male, yeah, okay. But if I were to say something like 5'7", who knows, right? And so these are really interesting problems that we run into. So again, I'll present some of my work and research that I've done because I think it's really interesting to statistics. One of the findings that my group had recently is we were looking at male and female students in computer science. And if you don't know, females in computer science, I think the number is like at 15 to 20%, I want to say. It's absurdly low. But the interesting part is women who go into computer science have higher GPA than the men. Women who graduate computer science have a higher GPA than the men. And perhaps even more interesting is that when women leave computer science, they still have a higher GPA than the men, right? And so one of the questions we were asking is what's going on? And so we used a lot of statistics like this where we tried to see could we clearly separate in the data what's going on with women, some of the statistics regarding women, and some of the statistics regarding men. And it ends up that you can't, right? And the big lesson for that was, unfortunately, it's the culture of computer science, right? So we tried to run every numerical analysis that we could to figure out why women might leave even though they're doing well. And you can't explain it numerically. So at that point, you're left with sort of social issues, which kind of makes sense because every piece of research right now says that computer science is heavily gendered and biased in the classroom and sort of the way that it works. Okay, anyways, that was a big aside, but hopefully at least a little bit interesting. So, all right, yeah, so one of the things that we try to do sometimes is understand these quantiles and percentiles. And it gives us an idea of where people are or the spread of our distribution. Okay? So if I were to say something like within 20% of the mean, maybe that's the mean. And so this blue part, this is our 20th percentile right here on the, oh no, not the 20th, sorry, 30th, right? Because if the median is 50 percentile, then the 30th, 20 away from that is the 30th percentile, right? And then 20 up would be the 70th percentile, okay? So maybe I'll say something like, oh wait, we never decided on a height. So let's say it's 5'6", just for fun, right between the two. We could say something to the effect that maybe the 30th percentile of students is 5'3", right? While the 70th percentile is, I don't know, 5'11", okay? And so this gives us some indication of the spread, right? And what fraction of our population lies between the 30th and 70th percentile. Now, why did I pick 30th and 70th? Because I felt like it, right? Traditionally, people use the 25th percentile and the 75th percentile, right? What they do is they divide up their data from some, minimum value to a maximum value, and they divide it into 4 equal chunks. So we know the middle is the median, right? And then they choose the 25th percentile and the 75th percentile, all right? These, because you're dividing it into 4 chunks, your data, right? That's why we call it quantiles. Or is it? Or, yeah, so we'll talk about the first quantile, the second quantile, the third quantile, and the fourth quantile. And in fact, the ones that most people are interested in are the first and third quantiles, okay? And nobody actually calls it the second quantile, they just call it the median. All right, so I think we went over to Excel at some point, and I was showing you guys how to calculate some of these values. Oh, not yet. Some stuff got lost, maybe. Right. And so, let's see. So again, I think this was actually not concrete data. This was the charity data. Okay. And so we might ask ourselves, well, what is the 5th percentile? What is the 25th percentile? 50th, 75th, and 95th percentiles. Okay. And so if we want to do this in Excel, we just say equal, and then I think percentile. All right. You use tab completion. You give it the column of your data, and you tell it exactly what fraction you want. Now I do remember this. So you could just write in 0.05 up there if you wanted to. Or what I'm going to do is I'm actually going to reference the column. All right, so I can go ahead and click on the column. And then the issue here is this is given 5, 25, 50, 75, 95. We need to get it as a fraction out of 100, so we're going to divide that by 100. Okay. And I can apply this equation by dragging it down. Okay. So what does this tell us? This tells us that the median charity spends 6.8% of their expenditures on fundraising. Okay. The bottom 25%, that is to say, 25% of the charities spend less than 3.875% of their expenditures on fundraising. Okay. If we want to see what the 5% is, 5th percentile, right? That's 1.3%. So 5% of charities spend 1.3% of their expenditures on fundraising or less. Okay? And so this is a pretty useful tool to help you find outliers. So a lot of times if you're doing, let's say, machine learning type work, one thing that people do is they collect data, and if they see data that falls outside of, let's say, the 5 and 95% percentiles, they'll just throw it away, right? So the reason why you actually might be acceptable to throw away is if you have some sort of measuring device, right? And that measuring device sometimes has like a short or, I don't know, data transmission issue. It just returns garbage, right? And if you recognize it's garbage, then you just say, okay, this is garbage, throw it out. The other reason why you might do this is if you're looking for anomalies, right? So I've been involved in some projects where we wanted to figure out, we had some rollers that were basically making metal sheets, stretching out metal sheets like aluminum or steel. And we wanted to look for defects in that metal sheet, okay? So we were measuring the thickness of the metal sheet, right? And so if we ever saw the thickness get too thin or too thick, then we knew we sort of had to stop our system and figure out what was going on, right? So sometimes you're doing anomaly detection in this way in order to figure out something bad that's going on so you can actually correct it. So it's not just throwing away data necessarily. Right. Okay, so there's percentiles. That's nice and good. And again, the idea is usually when we're talking about the mean and median, we're getting some sense of where's all the data located. All right. So the next big question is not just where that data is located, how is it spread out? Okay. We kind of touch on this with the quantiles, right? Because if you know your quantiles, you kind of have an idea of the spread, right? So here we have sort of 3 different examples from the book of data sets, okay? And so in this first data set, number 1, you can see the points sort of spread out, right? It has a high variance, right? Because, you know, it's sort of spread out. Variance is a measure of how far things are spread out, kind of. The second one has a smaller variance, right? It's still spread out, but most of the data is actually concentrated. And then finally, the third data set, with the circles with the blacks filled in, has the smallest variance, okay? Now, the interesting part is, it all depends on how you define variance, right? I think you could certainly make an argument that maybe 3 has a lower variance, or sorry, 3 has a greater variance than 2, depending on what metric you're using, right? But for our purposes and statistics, the metric that we use, 3 would definitely have a lower variance. Okay. So there's actually a few metrics to understand variability, okay? The first one is the range, okay? So range is what's my maximum value, what's my minimum value of my data set, okay? So if we were to use range as our measure of variance, right? Or I don't want to call it variability, sorry. Then 1 and 2 would have the same variability, right? According to the range, right? Because what we see is their largest value and their smallest values are both equal, okay? So when we calculate the range, which is the maximum minus the minimum, we're going to get the same value. So we can do this in Excel. Unfortunately, there's no easy function. Well, not to say that there's no easy function, but there's no one function that does it for us automatically. We have to type it in by saying, all right, give me the maximum of my data and now subtract off the minimum of my data. All right, and we'll get the range that way. All right. All right, so this is one measure. If you have a system with, let's say, outliers in the sense that like maybe you have a sensor that every once in a while it returns junk, right? Then the range is a very deceiving measure, right? You have to be careful, okay? But if you can trust the data that you're getting, then it makes some sense, right? So let me give you an example of this. Let's say I wanted to know what is the range of sizes for different animals. Okay, so for humans, I don't know what the tallest human is at, but I'm sure it's about 8 feet. Okay, shortest human is probably about 2 feet. Okay, so the range for humans is about 6 feet total. All right, now that range value assumes that I accurately measured the height of each one of those people, right? What if height is self-reported, right? And I ask for all this data, and I get everything looking good, looking good, looking good. 6'1", 3'2", 6'4", 5'2", 5'8". You know, I'm getting all my data, and all of a sudden, I get something like 160. In what world does 160 make sense? It actually does make sense. You know, here's what do I say it again?
Centimeters?
Yeah, centimeters. Yeah, so there's a case where if people are self-reporting, they're acting as a sensor, right? If I just process that data without even thinking about it, then I'm going to run into an issue because all of a sudden I think the range of human heights goes from 2 feet to 160 feet. Okay, so just be very careful about the use of range, right? Using range only really makes sense when you can guarantee the accuracy of the data that you're working with. If you can't make that guarantee, then actually what you can do is you don't necessarily have to use the range. You can use quantiles or percentiles, right? So one thing that I'll do is I'll ask what's the 5 to 95% percentile. I don't know what you'd call it. Right? Like I want to know what's the range of variability I expect to see in these charities, right? Or what's the range of delays I expect to see for airplanes? How big is it? You know, like, yeah. So I can just use the percentiles that I already calculated. So I'll just take the 95th percentile and I'll subtract off the 5th percentile. Okay. So that gives me some idea that around the median, right, of 6.8, right, 90% of my data lies within 25% of each other. It's useful to know. So, okay. Oh, I need my notes. So, some folks said, well, the range isn't a good measure because we know we're going to get bad data sometimes. So let's try to find a better measure. And so one of the proposals started focusing on deviations away from the mean. Right? So how far are you away from the center? Now, it could have been the median, for all we know, right? But they chose the mean. And typically, if you want to know why mathematicians do things, actually, what's any given the choice between A and B, why would you pick one over the other? I think people are motivated by about 2 things or 3 things. right? One of them is money, right? So I'd pick A because it's cheaper than B. What's the other thing? So again? Well, okay, that's another one. Yeah, so maybe that's, yeah. So we have fast, good. What's another one? Or yeah, the time it takes. What was the other one we said? Money? Oh yeah, time it takes. Right? How easy is it? Okay, mathematicians are no different. Okay? Most of the mathematics that we have derived is, especially equations like this, y is the variance equal to the sum of the squares of the deviations away from the center using the mean. It's done because the math works out really, really nicely. Okay, that's the only reason, or that's the biggest reason. Okay, when you're asking yourself, why is the basic deviation of variance defined by this equation? It's just because it makes life easier for other things. Okay, so that's normally how they work out. Okay, so we'll sort of talk about this and show why that's the case. All right, so normally we're talking about deviations away from the mean when we want to measure variance, okay? So let's say in this example, our mean is right here. Okay, so we'd measure, the distance from that center point to every other point, right? And we'd use that distance, right? We'd sum it up in some way, and that tells us how spread out we are. So we always talk about some center point, and then how spread out the points are relative to that center point. Okay. And we're going to try to sum these all up, all these distances, and that will give us a measure of variance. Okay. So again, mathematicians said, well, let's pick the mean because trust me, the math will work out easier for us later on. So we're going to look at the deviation of each data point relative to the mean. So if we collected data points x1, x2, x3, yeah, all the way to n data points, we're going to look at their deviation. All right? So, we always start with what the easiest thing to do is. So somebody said, well, maybe we could make the variance just the sum of all these deviations, because that will give us some measure of the spread. Now, the problem is that doesn't work out. All right, so let's say I said I want to sum I equals 1 to n of xi minus xn, or no, x bar. Okay, so I'm going to add up all these deviations. So I'm adding this, plus this, plus this, plus this, plus everything in between. All right, that sounds good and fine. So I'm going to work out the math. I'm sure you can sort of figure out the answer, but I think it's sort of fun to work out the math because some of these equations and the way of thinking will pop up again. So we can break up the summation into two parts. All right, so that'll be one summation. Right, and then we can break off this other summation. Okay, cool. All right, so one useful thing to know, if we sum some number, let's say I have the number 5, and I want to add the number 5 6 times, right? So I'm going to do 5 plus 5 plus 5 plus 5 plus 5 plus 5. What am I going to get? 30. All right, so all you're doing is you're taking the shortcut, is you're taking this number and multiplying them together. All right, so that gives us some indication of what the second summation is going to be equal to. All right, it's just going to be n times x bar, which again is the sample mean. Right? I gave a lot of data. I calculated the sample mean, and we can remind ourselves what the equation is. All right? It's just adding up all our data points and dividing by n. Okay. All right. That's cool. All right. So we can use that same equation on the right to tell us what this summation is equal to. And we can do that just by noticing, well, what we have written here is effectively what we have there. Okay, it's just the numerator of that fraction. So if we are to multiply both sides by n, we know that the summation of I equals 1 to n, xi is just equal to n times the mean. Oh, okay, cool. So we can substitute that value into the summation, and looky looky. All right? They're equal to each other, so they're going to cancel each other out. All right? So, excuse me?
Well, the math worked out.
Yeah, the math worked out, right? So if we ever try to sum up the deviations about the mean, it's always going to be equal to 0. Okay, so this was probably the easiest measure of variability that we could have outside of the range, and it doesn't work. Okay. So the next easiest thing, actually, what might you think the next easiest thing would be if I didn't say it was to square the deviations? Well, okay, let's get to that next maybe. So the next easiest thing that you can do, math-wise in the world at least, is to square the deviation. So before we had these deviations, and we just tried summing them up as they were. All right. Then some gentleman said, well, let's actually calculate the variance by taking the deviations, squaring them, and then summing them. And we're going to divide by n minus 1. We're going to ignore that for now. And we'll hopefully, there's a few explanations of why it's n minus 1. The one I'm going to give you in this lecture we'll reference back later on in the semester, and it makes most sense to me. All right. So the solution that they had was, we can't just add up everything, so we're going to square it first, then sum it, then divide by n minus 1, and we're going to call this our sample variance. Okay. So the thing that you always have to remember is variance is squared. You're always going to see that. All right. To make things a little bit more understandable, a lot of people will talk about the standard deviation. Oh, that should be deviation here. What did I have? Yeah. The sample standard deviation, right? And so they take the square root of this calculation here, right? You just get S. Okay. So why is taking the square root a little bit easier? Well, it kind of still keeps the numbers in a way that's understandable. All right. So let's go back to the heights. All right. Let's just pretend I were to tell you that, based on this data that we collected of heights of students, that the standard deviation is 6 inches. All right. That would mean the variance is 36 inches. Okay. So if I tell you the average height is 5'6", with a variance of 36 inches, actually not even 36 inches. What's the units on this?
Inches squared.
Inches squared. That's right. That doesn't really make sense. Okay. Nope, just inches. Okay. So generally people like to work with the same units that are consistent, right? So if I give you a mean height of 5 foot 6 inches, which is, what's 5 foot 6 inches? 66 inches? I think? Yeah. 66 inches. Then I should give you the standard deviation or some measure of variability in the same units, inches, not inches squared. That's really odd, right? Because normally what we're doing, and what we're going to come to later, is that if you take the mean, so 5 foot 6 inches, right, and you add one standard deviation, and you subtract one standard deviation, that accounts for about 60% of your data. And so that's kind of a nice thing to do, that we can just add and subtract and sort of know what range it contains. Right? But here, 36 inches squared doesn't make a lot of sense. Okay, so most of the time what you'll see is a lot of folks like working with just the standard deviation. Now, we do have to be careful. This is a sample, right? We're collecting data, and we're using our sample variance equation to estimate the spread of the data. Okay. Now, I think this equation is worth discussing a little bit more. All right, so again, what we have here is a spread. Okay. And we're summing up all those spreads. Now, let's just pretend we didn't have this -1 here. Okay. So if I added up the average, or added up all the deviations or the spreads, right, and then I divided by n, right, that kind of looks like you're trying to find the average spread of our data. Okay. That certainly makes some sense, and that sort of explains why we have this n-1 term. Okay? It's not just adding up the deviations that we observe in our data. It's adding up those deviations and kind of like averaging it out. Okay? Now, the -1 part, I don't know if I talk about it here. Oh, I guess I do. Is a whole nother issue. Okay. Now, what we're going to find in statistics is that this quantity right here comes up over and over and over and over again. Okay. And so what you'll see is that at some point, if you keep using the same equation over and over and over again, you define it. Okay. So in our case, we're going to define this SXX, right, to be the sum of the squares of the deviations, or this, yeah, sum of the square of the deviations. And this is a capital S. Okay, this is a big S. All right. The way this sort of reads is it's the sum of the squares of x relative to itself. Okay. Later on, we're going to see something like SXY. Right? But we don't quite need to do that now. The basic idea is we're going to see this quantity again and again down the road. All right, so again, the key point here is this is for sampled data. That's wrong. This should be variance. Okay. All right. So our sample variance is S squared. Okay. That's how we denote it with S. In the same way that we call our sample mean and our population mean different things, we're going to call our population variance sigma. Okay? All right, so again, we need to recall why we differentiate between the two. This population is everyone. Okay? With certainty, the height of every single student at UCF. The sample variance just refers to the spread if I were to ask the height of, let's say, 100 students or 1,000 students. Okay? Typically, again, what we do when we're sampling is we're going to sample our data in order to tell us something about the population, right? So, again, I ask maybe 1,000 students, how tall are they? I get an average height, average sample height of 5'6". That would lead me to believe that the average height of all UCF students is 5'6". Okay. So we're using our sampling data to infer something about the population data. In the same way, we can use the sample variance to tell us something about the population variance. So how is data spread, or how are the heights of students spread over UCF? Okay. And so really what we want is S squared should tell us something about sigma squared. Okay. So this is where the n-1 part comes in. Ooh, that's another little. All right. Let's actually start with the simpler one. So let's say I calculate the sample mean, and it should tell me something about the regular mean. If I changed, well, let's do this. Let's say I knew that the true value was 5'7". Okay. Now, if I sample 100 students, right, and I average their height, I'm not going to necessarily get 5.7. Okay, so ask 100 students, how tall are you? I get the average. Maybe I get 5'6", right? Maybe one day I'm standing outside of the football stadium when the football players walk out and I ask 100 people, how tall are you? All of a sudden I get 6'4", right? I don't know, I'm somewhere else and I get 5'2", 5'8", okay? So forth. Okay. If I average all these averages, hopefully I get 5'7", right? Or if I look at all the data together, hopefully I get something like 5'7". Okay. Let's say, instead of those values, I kept getting stuff like this. Would you have any concerns? I asked 100 people their height, and then I'd average those values, and I did that 6 different times. Would you be concerned with those values?
Yeah.
What's weird about them?
They all trend low.
They all trend low. They're biased, right? So maybe the way I'm sampling is actually biasing my data. Now, it ends up that the equations you use can also bring about bias. Right? And what we'll see is that if I were to instead, let's say I define sample variance, let's pretend. Okay, that I define sample variance as xi minus the mean squared over n. variance squared, sorry. So I didn't have this -1. The crazy part is, if I were to do that, there would be a very high likelihood that s squared would be greater than sigma squared. Or, sorry, less than. Less than sigma squared. We call this a bias estimator. Right? And the reason it's biased is because on average, if I were to use this equation, the sample variance I calculate would be lower than the actual variance of my population. And so this is bad. Right? What you want is for these values to be about the same, to overlap, right? S should be less than sigma as often as it's greater than sigma. Okay. Right? And the more data you get, you want them to actually start to lie on top of each other. Right? But if you use this equation, that's not going to happen. What's going to happen, well, with a lot of data it will, but what's going to happen is S will tend to be less than sigma. And there's a bias estimator. Yes, sir.
Is there like a reason for that?
Yeah, so we'll go through it in once we get to it. Yeah. So basically it underestimates the variance, okay? And so what happens is you can actually show, what we'll show later on, is that if you divide by n-1, it's an unbiased estimator. It's a fair estimator of the truth. And we'll work through that. Now, some people will relate it back to something they call degrees of freedom. And I've never quite understood this argument. I kind of miss it. But the basic argument goes like this. Let's say you have 100 data points. I have this equation here, s squared. Those 100 data points are used in the calculation of the mean. Right? I add up those 100 data points and then I divide by 100. And they refer to this as using up like a degree of freedom. Okay? This equation is no longer based on all 100 data points. It's actually based on 99 data points. Okay? Because you're using those 100 data points to calculate that x bar, that mean. And so that took away a degree of freedom. Right? So some people relate the degree of freedom to that denominator, right? Because it ends up the degrees of freedom is given by n-1 of this equation. So I think you guys have all taken algebra. So you always talk about like number of knowns and number of unknowns, right? It's kind of that idea. Or sorry, number of unknowns and the number of equations, right? Same idea. Okay? How many equations do you, or how many data points do you have? 100. How many equations do you have? You actually have two. You have the s squared equation, and you have the x bar equation. Okay? And that x bar equation sort of subtracts off some of the knowledge that you're getting from 100 data points. You don't actually have 100 data points of knowledge, you have 99. Okay? Because you had to use up some of that knowledge to figure out x bar. Okay. I might be bad at explaining that logic because I don't get it. Okay, so maybe you can talk to, I think the book might even discuss this argument. All right, but I think the bias is a better and stronger argument, which is to say, if we were to just divide by n, we would underestimate the population variance, the spread. Okay. All right. So what I want to do is kind of work through an equation that you're going to see come up over and over and over and over and over again, right? Especially if you go into controls or robotics or optimization, and even just in this class, this equation will keep coming up. Okay. And so it's worth understanding where it comes from. All right. So, and it sort of leads to, well, yeah, let's just hold off there. Okay, so what we're talking about is we have this summation of our deviations. Right? And I want to show that this property holds, okay, that these two are equal. So it's actually not too hard, but you just got to sort of work through it. First, we have to remember a couple things, what x bar is equal to. So it's the sum of all the x's over n. So all that we're really doing is expanding out our square and reorganizing a few things. All right, so, oops. All right, so if we expand out the square, we have the summation of xi squared minus 2xi over x bar plus x bar squared. All right. It's not too bad. Okay, so we can basically break this up into three different summations. The summation of xi squared, which is good because that's what we wanted. Oops. That gives us one of the things that we wanted right off the bat. Okay. Then we have minus the summation of 2xi x bar. Okay, and just to be clear, we're summing them over all the xi's plus the summation of x bar squared. Okay. Alrighty. So this value here, actually two values. So the value 2 has nothing to do with this summation, right? And this x bar has nothing to do with the summation, right? You're only incrementing the I, which is changing this xi value. So what that lets us do is sort of pull out these two terms. Yeah. Oops. So again, we still have the part that we want. Now we can pull out this x bar and the 2. And we're just summing up xi. Okay. In the same way, right? What was the trick we did before, right? This x bar is just a number, 5, right? If I sum up the number 5 from 1 to n, I get 5n, right? So it's the same little thing that we did. Where'd we do it? Over here, right? So we can apply that. And we just get n x bar squared. Okay. So we're adding up our mean squared n times. That makes life a little bit easier. In the same way as before, we can notice that the summation of xi here is just the numerator right there. Okay, so if we multiply both sides times n, right, we know that x bar n is equal to the summation of xi. So we can use that knowledge to substitute in here for the summation. Yeah. So when we do that, we're going to substitute in n x bar. Now we have n x bar squared. Okay. So we can take our two x bars. X bar times x bar is what? X bar squared. And let's reorganize this a little bit because I wrote it badly. We have 2n x bar squared plus n x bar squared. So these two guys are the same, all right? But one is minus 2 and the other is just plus. And so we are left with the summation of I equals 1 to n xi squared minus what? Nx bar. Yeah? All right. So this is actually a really useful trick, this equation right here. Just this part itself is useful. Okay? Because the neat part about it is, if I want to calculate the standard, or the sample variance, so normally the sample, let me write this in a different font. Well, actually, hold on. We'll just finish this work off. Okay, so what we wanted to get to was, again, this equation. We need to get this right here, but it's not too hard because we just use the definition of the mean again, this guy. Okay, but now we're squaring everything. Right? So we can go ahead and just use that substitution. Right. Ooh, what's x bar equal to? It's the summation of xi over n, and now we're squaring the whole thing, right? Oh, times n, thank you. It did look a little funny. Times n. Okay. So what we're going to end up with is we're going to square this summation and square the n on the bottom. That means only one of the n's will cancel out, right? So then at that point, that gives us what we want. Oops. Okay. So I do want to give a big caveat because I noticed this. Do any of you guys have these notes printed out? Oh, okay. Well, I will tell you this. All right. In OneNote, you see how I have the x squared outside of the parentheses, which is correct. When I converted this file to a PDF, so if you download it from web courses, you're going to see that square, this square inside the parentheses. So it's going to look like the sum of xi squared. That's wrong. I don't know why Microsoft translates its own equations incorrectly, but it does. So just be aware of that. Okay. All right. So we did that little proof, and we did that proof because it's going to keep coming up over and over again. Yes, sir?
Is that something we will be expected to be able to prove on a test?
No. Appreciate it. Try to remember it, so then when you keep seeing it, you can go back to that. Okay? Unless you guys want written exams. Because as of now, you guys have web-assigned exams that are auto-graded. It's up to you. I actually don't mind written exams. I think they're a little bit more fun. Does anybody want written exams? No? You guys feel comfortable with web-assigned? Or will, hopefully? Okay. Yeah. Okay. Given that most of the class is statistics, which are calculations, it doesn't make sense to have a written exam. Just my thoughts. Okay. Oh, we don't have that much time on. Okay. All right. So why is this equation useful? All right. So normally, if we wanted to calculate the standard deviation, we would have to do a whole bunch of work to calculate it here. Oh, you guys, actually, you can't appreciate this unless you're doing it by hand. Okay, so when I took probability and statistics, I had to calculate this by hand. Okay, so imagine you had a bunch of, let's go to this charity example. All right. I would be given about 20 data points. Right? I'd have to calculate the average, so maybe my average was 6.6. Right? And then I would have to take all these values here, subtract 6.6, square it, right? So now we're squaring decimals, and then add those decimals all up, and then divide by n minus 1. Okay? When you're working with decimals, that's like a whole lot of places to make a mistake. Okay. The nice part about this equation right here is it simplifies the number of operations that you have to do. So before you were always taking x, your data point, and minusing the mean. X minus the mean, x minus the mean, x minus the mean, x minus the mean. Square, 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 square. Add, 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 add. Divide by n, or n minus 1. Now let's look at this one. Okay? And just to be clear, I'm going to put the parentheses right there. Okay? In this case, this is the same equation, basically. This is what we just showed. All you have to do is square all your data and add it up, which isn't, I mean, it's not great, right? But it's easier. It's one less operation, right? You're not having to subtract off the mean every time before you square it. Because the other issue is, normally, so if I had a problem and calculating the variance was one of the problems, right? Guess what the problem before it was? Finding the mean, right? So I had already done that calculation. So now I just have to subtract it off. So that's why this boxed equation is especially nice. If you're doing these calculations by hand, it's way easier. Yes, sir?
Never mind, I actually answered my question.
Yeah. So it's funny now that I think about it, because I think a lot of this stuff we learn, again, was to make life easier for us, because we were doing a lot of these calculations by hand. We didn't necessarily have Excel. Okay. All right. So we're going to do another derivation. And again, the reason why we do these is because this is an honors class. And these are the types of skills that you're going to need to learn down the road. Right? So I want you to hopefully appreciate some of this stuff. Okay. So what I want to show you is what happens to your variance and your mean if you transform or rescale your data. Okay. So let's say xi, here's a good example. Xi are a bunch of temperature measurements, but maybe that temperature is in Celsius. Okay. And I say, well, I want to know the mean and the standard deviation in Fahrenheit. Okay? And so I'd rather have the data in terms of Fahrenheit, degrees Fahrenheit. Okay, so I think we have some equation for that, which is, what is it, 9/5 xi, is it plus 32, is that right? Yeah, so there's our equation. So if I told you that the average temperature in this building, thankfully it's much cooler today, is 72 degrees, right? And the variance is 3 degrees. Or actually, we should do it in Celsius, right? So it's 1 degree Celsius variance and 25 degrees Celsius for the average. I don't know what that means. I want to know it in Fahrenheit. I'm not British or French or whatever. Right? I was born in America. Yay, America. Okay. Actually, funny story. When I was a little kid in the 80s, Congress passed a law that we were supposed to do everything into the whole metric system. And so for about a few years, they tried teaching every kid how to do like measurements in metric and teach us Celsius and like milliliters. And what ended up happening is all the parents complained because they couldn't help the kids with the homework. And so I think everybody, what did you guys learn it in? Like, did you guys do those things where you measure things? Did you do it in centimeters or? Like, and I mean like in 3rd grade and 2nd grade.
No.
What? What was it in?
All inches and feet.
Inches and feet. Yeah, so when I was in 2nd grade, they had us doing everything in the metric system, which is like super confusing for the parents for some reason. Okay. Anyway, so this is the world we live in. I don't know. What were you saying?
They said never use the side of the ruler that has more lines on it. Just use the one with
Yeah, exactly. Right. Those, Yeah. So we're working in that framework. Okay. All right. So the question is, how do I calculate or understand what the mean is and the sample variance if I have to do this transform? Do I actually have to translate all the data and then recalculate the variance and recalculate the mean? Okay. What I'm going to show you is that there's actually a nice little rule, right, that tells us how the mean changes and how the variance changes. Okay? And it's actually not too bad, all right? At least for the mean, it works out pretty nicely. So the first question is, what's y bar? Okay, so I'm just going to use a generic equation where it's ax plus b. All right? And so we're still going to use the same idea that our mean of y is just the sum of all the yi's divided by n. Well, we have an equation for yi. We can substitute that in. And we can start splitting it apart, of course, like we've just been doing all lecture today. All right, so that's nice. All right, and now we can actually start calculating some values. So here we can pull out the a, and we have the sum of xi over n. Okay, so I'm going to split this fraction up. And here I'm going to have b, which is a given value. So if I'm doing the summation from 1 to n, I just end up with nb. Right? And I'm going to divide by n. So these n's just cancel out. Right. What is this quantity equal to? It's x bar, right? It's the average value. So we're left with y bar is just equal to a times x bar plus b. That's not bad. So if I know the average temperature, let's say is 25 degrees Celsius, then I know that the average temperature in Fahrenheit is just 9/5 times 25 plus 32. Whatever that is. I think that's about 72 or something like that. Okay, so if you guys are patient with me, I'm sorry, we're going to go over a minute. Okay, so the next question we might ask is, well, what's the sample variance of y? Right. So we're going to apply the same equation more or less. Right. And now we're going to be adding or taking the sum of yi minus y bar squared, okay, all over n minus 1. And we can do the substitutions that we have before for both y bar and the yi's. Right? Yeah, it looks about right. Okay. And we can start actually, what I'm going to do is I'm going to group all the A parts with A parts and the B parts with the B parts. And in fact, the B parts just cancel out, right? So because we have the subtraction here, we're going to minus the B and minus the B. So it's gone. Okay. So what we're left with is AXI minus AX bar squared over n minus 1. Okay. We can pull the a squared out, or the a out of here, and that's just going to get us a squared times the summation of xi minus x bar squared over n minus 1. We already know this quantity. This is just the sample variance of x. Okay. That's a little s, just to be clear. And so what we'll find out is our sample variance of y is given by a squared times the sample variance of x. Okay, so if I want to know what the standard deviation of our y data is, we just take the square root. So we're going to take the square root of this guy here. Okay. And we have to be careful because a could be a negative number. Okay? There's no reason I'm saying it's positive. So when we take the square root of a squared number, we just get the absolute value. Okay? So this is the sample standard deviation of y after a transform. Okay? So again, if I measure it in Celsius, all right, and I told you the deviation was 2 degrees Celsius, and I asked what's the standard deviation in Fahrenheit, it would be 2 times 9/5, whatever that quantity is. Okay, thanks guys. Sorry about running over.